Okay, Bismillahirrahmanirrahim. Salatu wassalamu ala Mursaleen, Sayyidina Muhammad, wa ala alihi wa sahbihi ajma'in. Assalamu alaikum, everyone. Okay, so today, inshallah, we're going to be continuing with the localization topic. And today, starting today, the lectures will be dependent on each other. Okay, so until the end of topic number 4. Okay, because we're going to start talking about Kalman filtering, and today will be just prep work for this topic, for this localization algorithm. And it's very important that you really start, connecting the dots and start studying, on early basis. And that's why I'm going to start recording the lecture only for this part. If you like it, we can continue till the end of the course. But at least for this topic number 4, it's very important that you come every lecture, prepared with what we discussed so far. That includes also the assignments and the homeworks, as you're going to be seeing, inshallah. So let's recap what we discussed so far. So we said that in the localization, the way we're going to be doing localization, we're going to be representing the belief of the robot about itself, not just by one position. The robot will not think it's in this position and with this orientation. It will have an infinite set of positions, and we're going to be representing it by a probability distribution function that will describe here the belief about the robot, about itself, the representation of the belief, and this will be given by a conditional probability of where the robot is, of the state of the robot X, given all of the kind of information that we have about how the history has been going. And today we're going to be formalizing this properly, inshallah. And we said that this probability distribution function, we're going to be doing everything with the Gaussians. Gaussians will be the easiest thing to work with. And this was the equation for the multivariate Gaussian, as we discussed so far. It's an equation that it's a function of x, where x here is a vector in Rk, and it's determined by only two parameters: the mu, the mean, which is another vector, and the covariance matrix. And we said the covariance matrix relates every two elements between x inside of x. So x with it. So first x1 with x1, x2 with x2, and so on. But also x1 with x2, x1 with x3, and so on and so forth. We said that the joint probability, so this was what we discussed last lecture. It was a little bit of basics of statistics theory. When we looked at the joint probability is a function of two parameters, two or more. Okay, so here we have two random variables, capital X and capital Y, and they can take on different values. And we said that the joint probability is simply the probability that X happens and Y happens, at the same time. And we said that when we sum over X and Y, if we have a discrete probabilities, they must sum to 1. And if we integrate, the equivalent is that you do double integration, and you get 1. So for all variables, it could be X, Y, and Z, and so on. You can have many random variables. The marginal probability is simply when you sum over one variable and you leave the other one, independent. So here the P of X is simply called the marginal probability that X happens, and it's simply given by the joint probability that X and Y happen after you take all of the possibility of all of the possible Y's. And the continuous case is simply just integrate over dy, and the other you can do it for any variable by keeping the others fixed. And the conditional probability is simply it's a function. The conditional probability is a function of one variable or two variables. When you look at it like this, is it a function of one random variable or two random variables?
Two random.
No, one random variable.
Why?
It's a function over x given that y happened.
Okay.
So as a function, it's a function only of the x. The y has already happened. It's like an input to the problem. It's no longer another random variable that you need to consider. So it's not a part of the function. This is only a function of x given that y happened. So this is the notation that you see here. And we said that the relation between the marginal probability, the conditional probability, and the joint probability is given by this formula, which simply states that the ratio between the joint probability of x and y to the marginal probability of y is what defines the conditional probability of x and y. And we will look at today, before we're looking at how we can use this probability to do localization, let's look at something called Bayes rule, which is very important, and it will just finish up this idea of the basics of statistics theory that we need to understand really how we're going to be using it later for the localization, which is for the robotics side. So we're going to be starting from this last formula we just mentioned, that the conditional probability is equivalent to the ratio between the joint probability of x and y to y. And you can see here, if I actually, this is p of x and y, and this is division by p of y. I can also redefine it as p of x and y division by x, and the only thing that will happen is that here these two will swap. So here this was the conditional probability. It's a function of x given y, and this is the conditional probability as a function of y given x. And it's very easy that actually you can combine these two equations, okay, and you can get this formula in the end. Very simple. Mathematically, it's just, it's one line, but this is actually an extremely powerful equation. Okay, it's sometimes overlooked, and you really need to get your head around it. We can spend really a lot of time just trying to go into the details of what this means, but instead we're going to be looking at it in action. We're going to be seeing how this is used actually to do robotics. This is known as Bayes rule, okay, and we just like Bayes theorem. So Bayes is the name of the scientist, the mathematician that was studying this field. And this equation says, and we're going to look at it in some details, is that mathematically it's very easy, right? So let me give you just the pattern how it mathematically works. It just says that if you want p of x given y, you can compute it from p of y given x. So it's like you just swap the x and the y, multiply by the p of x. So the p of x here is the probability of the data of the x, the one that's that's given, that already happened, divided by the p that y happened, so the marginal probability of y. So the conditional probability of x given y is equal to the conditional probability of y given x multiplied by the marginal probability of x divided by the marginal probability of y. Okay. Mathematically, it's very simple, but let's try to go into a little bit of details. What's the intuition behind what that means? This equation is extremely important. It appears in statistics, machine learning, and robotics. We're going to be using it for robotics, but it's a really very fundamental theory. Okay? And you use it a lot in algorithm building and so on and so forth. So these are the names of the different types of probabilities here are simply what we already discussed. So this is conditional probability, this is conditional probability, this is marginal, this is marginal. So that's it. Okay, so there's nothing new there in terms of the type of probabilities. However, we're going to be giving them different names and how they appear in the equation. First, we're going to be calling the p of x here the prior probability. Okay? It's a prior. You know what prior is? Before. Something that happened before. Something that we already know. Something that happened and we already know about it. So we already know that x happened. You remember here in this right-hand side, we said x happened already. Okay? And x was already another random variable. So it has a probability of its own that it might happen. So this is the p of x here. It's the probability, the prior probability of x before anything happens. This is what we came up with. And p of x given y, so the left-hand side, is called the posterior probability. What does posterior mean linguistically? After, exactly. So there's something before and there's something after. Before what and after what? What is it? Can you try to get it from the equation?
For example, px given that y happened, that y happened before the probability of x to anyone, whatever it is.
Y happened is the event that we're talking about. So when y happened, there was some stuff before it and some stuff after it. So this term is what? Is it before y or after y? After y happened. And the p of x is before y happened. Okay? So p of x is the prior, p of x given y is the posterior after y happened. And now we divide by the probability that y itself happens, this event that we're talking about. And the last thing is this term here. It's very important, and it's usually called the likelihood. The likelihood is simply what is the probability that y happens given that x happens. Okay? It's a lot of it's mouthful and it's very confusing. The first time I heard this, it took me many times to hear this actually. And this happened not during one course. The first time I heard this stuff, it was very confusing. I did not know what it means, so I completely understand the look on your face. But let's move on. Okay, so if you just read what all of this stuff means, you'll find that okay, they make sense. But how does it fit, in robotics and so on. This will hopefully by the end of 3 or 4 more lectures just hearing the same stuff. So for now, just know the terminology, and what I want you to get out of this slide is simply just the order. Okay? And the order is simply very easy. P of x given y is equal to P of y given x multiplied by x divided by P of y. Even we're going to be simplifying it a little bit. So there's a much simpler version especially when we come to work and to do calculations, that the P of y itself, we're even going to forget about it from the equation. We don't even need to know the P of y. The reason is the following. P of x is a probability, right?
Yes.
And it means that it has to be integrated to the integral of P of x with respect to x. What should the value be?
Constant.
What is that constant?
1.
Exactly, should be 1. The probability that x happened is 1. It's 100%, given all of the values. So P of x is a probability, multiplied by P of y, which is another probability, another probability function. So when you multiply two probability functions together, the result, is it automatically equivalent that can be integrated to 1? In general, not. But the left-hand side, it has to be another probability function. So simply, when we divide here by P of y, we can easily just multiply, we can assume 1 over eta, so we can assume 1 over eta to be equal to P of y, or 1 over P of y to be equal to eta. And simply, when we multiply these two pieces of information together, we can calculate this in a post-processing way. Okay? So after we calculate these two, we just calculate this, and such that this has a probability. It's a probability function, so that it can be integrated to 1. Okay? So this is a much easier version of the Bayes rule, which simply says that if you want that, I'll rephrase it again. P of x given y is simply P of y given x multiplied by P of x. Okay? Multiplied by some factor that will normalize this probability distribution function. Easy? Okay. On its own, it's easy. Okay. How does this fit into robotics is the hard part that will require some time. Okay. So now let's take a small example, and this is really a fundamental example that will build a lot into really something that we're going to be taking this small example and go till the end to drones. Okay, how can we actually what we've seen before about fusing the IMU? How can you fuse actually different sensors together? So this is the starting point. So keep attention. Okay. So what we want to do here, what we want to model here is where the robot is in the environment. This is a very simple robot. It's a 1D problem where the robot can be anywhere along this line. Okay. Where the robot is physically is actually in this location. This is where it actually is, but we don't know that. Okay. And thus we were going to be representing where the robot is by a probability distribution function. You see here this bump here. Let me write on the slide. You see here there's a function given by this. You all see it in the equation? This bump? Clear for everyone? This is where the robot, where the robot thinks it is. Right? So the robot doesn't think it's in one point, as we mentioned. It doesn't have a single hypothesis about where it is. It actually has a multiple hypothesis. And this is given by the function. Where is the mean of where it is? It's given by this location, right? So this is where it most likely thinks it is, but it actually has some sort of plus or minus. It has a standard deviation about where it thinks it is. Okay? So it knows that there's a 90% chance, if you remember, that it can be within this region, but it doesn't know exactly where in it. Okay? So this is what the equation means. Okay? 90% chance it's in this region. If you reduce a little bit more and more, okay, the percentage, okay, the percentage starts to decrease. So this is where the robot thinks it is. The robot usually has on it what? That it will use to know where it, to actually identify where it is. What does it use? From what's inside of the robot? Sensors, exactly. Each one of these sensors that it has, is it perfect? So for example, when you measure from an IMU, when you measure from the accelerometer, in the x direction that you measure 0.1 meter per second square, does this mean that the acceleration of the robot in this direction is that number?
No.
Why?
There is multiple reasons, but one of them is the noise, maybe.
The noise, the misalignment. You remember what we discussed before? Misalignment of the sensors, the noise in the sensors, the bias, and so on and so forth. So there are many stuff that we saw. Some of them we can remove by what we did. What do we do to remove some of these effects? Calibration. So there's the calibration before you use the sensor. Does this make it perfect?
No.
No. We still, even after calibration, you're always gonna get, if you read from a sensor value, you'll always find something like this. So this will always be the acceleration in the x direction that you read from the accelerometer. So this signal here, we're gonna be approximating it by, so it has, so for example, this is the mean of the signal, and it has a plus or minus standard deviation, or standard deviation squared, it can be a variance. Okay? But not only that, if you have, for example, acceleration in x, acceleration in y, and acceleration in z, I don't just have 3 independent Gaussians, I have 1 Gaussian over all of them, because I start to have covariance. So a reading in the x affects the reading in y, the reading in y affects the reading in z, and so on. Okay, so you start to have this cross-coupling that was in the covariance matrix. So in the end, the readings here, you can always identify, you can assume, and this is the assumption you're going to be doing, assume that the readings that you get from the sensor is also given by another Gaussian that you see here in blue. So the Gaussian that you see here of the sensor is this one, is the Gaussian that represents the likelihood of the sensor. So you see here the prior belief, which is the one that we drew on the top in red, this is the P of x. It's the prior belief about where we think the robot is. Okay? And by we, actually, it's like the robot thinks this is where it is. Okay, so this is the prior belief of where the robot thinks it is. The likelihood, which is the blue one, is the probability that when you get a reading z, the robot is really at the position x. Okay, which is again the same question I asked you. So when I get the reading, for example, that if I get a reading of this point, for example, that at this point I get a reading of 0.1 meter per second square, does this mean that the actual acceleration of the robot is 0.1 meter per second square? And you all said no. What could be the actual reading here? It could be the mean, but could it be something else?
Yes.
Yes. For example, this could be, for example, that you took the robot and you placed it on a flat surface and you left it. You did not do anything. Okay? So it's not moving. And still it's giving you 0.1 meter per second square, right? And so on and so forth. So the true value here is 0, even though I'm reading some number. And even this number starts to change with time, okay? It starts to fluctuate. The same can be here. So this is exactly what you see here. So even though the robot is here, the sensor can tell me, okay, can give me all of these values here, can start to fluctuate around all of these values. This is what this picture means. The question is now, if I have the prior of where the robot is, and I have the sensor readings, is there a way that I can combine both Gaussians, or both probabilities in general, and get another estimate that's better? And the answer is yes. What do we use for that? So the question is, how do you combine both pieces of information? How do you combine what you already know about where the robot is and where the robot actually is? Okay, so sorry, how we combine what you know about where the robot is and what the latest evidence you got, the latest sensor reading that you got. How can you combine this? And the answer is, any guess? What is the mathematics that will help us combine these two Gaussian, combine these two PDFs? The Bayes rule, exactly. So take this probability, multiply by this probability. So take this probability, multiply by this probability. Of course, the result of multiplying both will not be a probability. Okay, so it will not sum to one, it will not be a function, but we can always normalize that by some value eta. We can calculate this in practice, and then what we're going to get is another probability function. The probability that you see here is called the posterior, and it's the one given below here. So when you combine where the robot thought it was with the new sensor reading, it has a new probability, it has a new belief about where it is. Okay? When you look at this figure, this is something that from what you already know. When you look at these three figures, can you say whether that the robot is more certain about where it is now or not?
Yes. The third one is more certain.
Why?
It has lower confidence rate.
And what does that mean? So here, what is the value? So for example, if this is a Gaussian, this is a Gaussian, and this is a Gaussian, which one has the lowest variance?
The last
A, B, or C? Typical question.
one. C.
Which one has the lowest variance? What was the variance? It was the standard deviation square. What was the standard deviation?
Control the either it's narrow or
How much the Gaussian was wide, right?
yes.
So which one of these has the narrowest Gaussian? C.
C.
So which and the narrower the Gaussian, it means what?
Also certain.
More certainty, exactly. The wider means more uncertainty. The robot doesn't know where it is. Exactly. It's less confident about where it is. Again, compare it to what we discussed before on Google Maps. If the circle is big, means that your phone is not able to identify where it is. But when it becomes smaller and smaller, means that it's telling you it's more certain that you're in this location. That's the same here. Okay. So is this just a figure or this always happens? That's a very important question. So we can draw whatever we want here. Is there a mathematical way to actually prove that when we combine two Gaussians together, we get a better Gaussian, and better means that we get more certainty? Let's look at this case. Okay, this is a special case, and just to do some calculations. When we have Gaussians, this is what we had in the homework, in the assignment actually. So you had this problem in the assignment. If you already solved it, okay, this will make sense to you. If not, you can go back and after you solve the assignment for the deadline. Okay, come back to this slide and you're going to see why what you were doing in the assignment was important. So again, let's just recap. The Bayes rule is simply multiply two probabilities together and normalize such that the result is another probability. It's as easy as this. In the case that the prior is a Gaussian, the likelihood is a Gaussian, then the product of two Gaussian functions is another Gaussian. So this is not in general. Okay. So if I have two PDFs of some type and I multiply them together, I don't get the same type always. But if you have a Gaussian, the product of two Gaussians is always a Gaussian, which is something very strong, okay, something very nice. Now let's take this example. Okay. So mathematically you can actually prove it, and that's the assignment. If I have two probability distribution functions, the two dot ones, you see here, for example, let me highlight them in the plot. So the two, if I have P1, which is given by this, let's take this orange PDF. So this is P1. Okay. And I have a blue one, which is P2. And I multiply them together by Bayes rule. What do I get? I get the black solid one. Okay. Mathematically, as I mentioned, so if the first Gaussian was what had a mean of Q1 hat and a variance of sigma 1 squared, and the other Gaussian, which is the blue one, had Q2 hat and sigma 2 as Q2 hat as the mean and sigma 2 square as the variance. So this one has sigma 2, this one has sigma 1, this one has a mean of Q1 hat, and this one has, actually, sorry, there's actually something here. Yeah, so there's something actually wrong in the figure, at least with the, so actually this should be P1 and this should be P2. Okay, yeah. So this should be P1 and this should be P2. There's a typo in the figure. So P1 is the blue one, P2 is the orange one. If I multiply them both together, you remember the Gaussian itself had an expression, right? It was the exponential of blah, 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 some stuff like this. If you take this expression and just, simplify a little bit the expression and use the exponential properties, that's exactly what you do in the assignment. You can show that the result, which is the product of P1 and P2, is another Gaussian that has a mean of Q hat, this green expression, and it has a variance of sigma squared. And sigma squared is simply given by, so the variance of the new Gaussian is simply the variance of the two multiplied together divided by the sum of the both variances. Sigma 1 squared, sigma 2 squared divided by sigma 1 squared plus sigma 2 squared. Make sense? And if you take this sigma squared, you see all of this value. This expression is sigma 1 squared multiplied by sigma 2 squared. The mean of the new signal, of the new PDF, will be sigma 2 squared divided by the sum of the variances multiplied by Q1 hat plus another constant, which is sigma 1 squared divided by the sum multiplied by Q2 hat. So you see there is a pattern here. The variance is simply the product of sigma 1 squared and sigma 2 squared, the product of the variance of the two original PDFs. And here I have the mean is simply Q1 hat plus Q2 hat, but they are weighted by different just numbers. Okay. So sigma 2, we're going to focus on something only one thing in this calculation here, which is this expression. Okay. Do you think that, let's try out with some numbers. If sigma 1 squared is 1, okay, and sigma 2 squared is also 1. Okay. So they had the same width, both the PDFs. So 1 multiplied by 1 is 1. Divided by the sum of 1 and 1 is 2. What is the new variance? Half. What does this mean? That after I combine both Gaussians, that each one had a sigma squared of 1, do I become more certain or less certain?
One is like a special case.
One is a special. Answer that question first. So this had a variance of 1. This had a variance of 1. The multiplication of both, does it have a bigger variance or a smaller variance? Smaller variance. Does this mean am I more certain or more uncertain? More certain. Everyone agrees? Make sense? So let's see if there's a special case. Choose any numbers. 2 multiplied by 2.
Sigma is 4 and 4 by 4 is 6.
No. Choose the sigma just to make it easier. It doesn't matter here. So choose the sigma 1 squared to be 2.
Okay.
So 2 multiplied by 2 divided by is equal to
1.
So am I better or worse? Better. Am I more certain? Yes. Smaller value. Maybe because we chose numbers greater than 1. Let's try to choose numbers less than 1. Half and half. So half multiplied by half is 1 over 4. Divided by 1. What's the result? 1 over 4. Is it less or less or more? Less. This is always the case for all numbers. The product of any two numbers, any two positive numbers divided by the sum is always smaller than the two numbers that you started with. It's like simple. It's not just math here. It's actually something very strong, and this is the conclusion of it. Why is this very important? Is because the uncertainty is always reduced by fusion. This is the key takeaway. Whenever I fuse two Gaussians together, imagine that one of them was a PDF from one sensor and the other one was a PDF from another sensor, and now I combine both sensors together. Even if each one was noisy, when I combine both together, I get less noise in the product. I get more certainty in the product. So the product of two Gaussian beliefs gives a more certain estimate because the resulting variance, the variance after I multiply both together, is smaller than either one of the original variances. So the lower variance means lower uncertainty, so the fused estimate is more confident. I get better results. If I'm using this for localization, the robot is more confident about where it is. Not only that, actually, you can take a look here, but this is harder to just see immediately. But the mean here will always be between both means. So for example, if sigma 1 hat was here, sigma 2 hat was there, the resulting mean will always be somewhere in between. It will not be, so it depends on the variances. Actually, it depends on these two numbers. It will either be closer to this one or closer to that one or in between, depending on the ratio here. Okay? So depending on these two constants. If these two constants are exactly the same, then it will be exactly in the middle. If this one is bigger, then it will be closer to Q1 hat. If this one is bigger, it will be closer to Q2 hat, and so on and so forth. Okay? Which means that the mean, also the fused mean, lies between the two original ones that actually balances the both sources of information. So going back to the problem now, if I have a sensor that's, now go back to this problem of the robot localization. If the robot thinks it is in this location, okay, some mean and some variance, and the sensor tells it it's actually a little bit shifted, okay, with a different variance, combining these two by Bayes' rule will always be somewhere in between. The mean will always be somewhere in between, and the certainty will always be better from both cases. Okay? So this is actually not a picture. This is really what happens, okay, mathematically. Okay? Is this clear? Intuitively, at least. Clear for everyone? This is very important. Okay, so it's really important that you really get this takeaway message. Clear? Everyone? Mohsen? Yes or no? If you want, we can repeat it. Repeat? Repeat. So, which part? Not all. Okay, at least start from somewhere. Okay, let's take the different bits. Is it clear that when I multiply two Gaussians together, I get another Gaussian? This will not be mathematically, so you only know it as a fact now. In the assignment, you will be proving it by yourself. You're actually calculating exactly what it looks like. So this you're going to be taking care of. What is the result? This is the resulting mean, the resulting variance. Is it clear from the example that we just did that the resulting variance will always be smaller than the two original ones? Is this clear? Smaller. The resulting variance will be smaller, which means that the peak of the combined PDF will always be higher. Higher and narrower means variance is smaller, remember? Right, so less variance, less standard deviation means the PDF will be narrower and taller. So this is what you see here, which means that it's more confident where it is. If you look at it in terms of Google Maps, the circle becomes smaller and more, smaller, and also it becomes pointing towards a certain location. It's more confident. This is what it means. Clear? So is this part at least clear? Everyone? Now, the result about why is this important is that, now going back to this example, if this was the prior about what we know where the robot is, so some PDF, some mean and some variance, and this is the value that we get from the sensor, combining both using the multiplication, this Bayes rule, which is just multiplication of the PDFs, will be more certain, and it will be in the mean that will be like somewhere in between the two PDFs. Clear? Okay. So that's what we discussed so far. Any questions before we move on? Okay. Okay. Now let's look at Bayesian filtering. All of this was just Bayes' rule. We took a simple example. Let's take how we can take this simple example and we can make into it something that the robot can always know or can always update. So we need to actually make it into some sort of like algorithm or some sort of like some recursive way of how the robot will always be able to know where it is. Okay. So, first of all, what does the word filtering mean? So you're going to find there are two, we're going to be using this word a lot. So the most important algorithm of the course is the Kalman filter. It's called the filter. And A more bigger umbrella, like as a framework, is actually called Bayesian filtering. When we say filtering, what comes to your mind when I say a filter? Sorry? That's a physical filter, like in a car or something. But that's in terms of a database. Okay, that's correct. Both are correct. But in terms of a signal processing, what comes to your mind of a filter? Sorry? Clearer data. Okay. So you're almost. Muhammad? Smoother signal. So if a signal was, very noisy, a filtered version of it would be, maybe smoother. It's like a smoothing operation of the signal. Yeah, so that's right. So you all know what a filter. If I can give you two signals, one is filtered, one is unfiltered, you'll be able to identify which one is that. Okay. That's not.
هل هو يترك النويز نفسه tuned ولا اللي فيها نويز يتركها كامل؟
That's an excellent question. Neither. In terms of signal processing, this is what filtering is. You're all correct. But in terms of state estimation, what we're doing right now, filtering is something different. The word filtering means something else. And that's exactly the definition of it. So filtering is simply when you have a sequential process of maintaining a probabilistic model for a state X, which evolves over time and which is periodically observed by a sensor. So the general filtering problem can be put into a Bayesian form. So filtering in general is simply that. I want to know how the robot's PDF, how the robot's belief will change over time. I'm trying to predict it. I'm trying to model it mathematically. How it will change over time. And every now and then, I'm going to get a reading from a sensor. Okay? And you'll see why every now and then. I'll tell you exactly why, maybe next lecture. So every now and then, we get a reading from the sensor, and we always update where the robot thinks it is. Okay? So there is always this idea of there is an evolution of where the robot, okay, of how where the robot not where the robot exactly is, but how the robot's probabilistic model. Okay? The probabilistic model here is given by the probability distribution function. For the examples that we're going to be focusing on, the state X that we're always going to talk about is simply the robot state. Okay? And when we say robot state, we're going to actually mean something very easy. It's just the robot's pose. So if I have a robot on the ground, a wheeled robot, then the pose is simply given by psi in the X direction, the position in the X direction, position in the Y direction, and the heading of the robot. And if I have an aerial robot, if I have a drone, then the pose of the robot or the state of the robot will be given by the psi and the rotation matrix. So just the generalization of the head. Okay? So this is what we mean here by the state of the robot. This is not, by the way, sensor fusion and filtering is a much bigger problem. Okay? It's much more general than this. We're only applying it to estimate the state of the robot. You can generalize this to be as much more. So we can actually put inside of the state here many more stuff. And this is we're going to be doing it actually later when we look at the sensor fusion problem. When we want to actually build an algorithm, a practical algorithm, to fuse the IMU together to get better estimates of where, for example, how the orientation of the you remember the Pix Hawk on the robot, for example, then the state of the robot will have more stuff, but more on that later. For now, whenever I say the state of the robot, you only think about the position of the robot. We're going to be taking some 1D problem, 2D problem. We're going to be taking some toy problems to understand how this evolves on it. So that's for next, inshallah. From now on, because we're going to be implementing this algorithm in discrete on a computer, we need to discretize actually the system. So whenever we say at time tk, we're going to always say the kth sample. So tk, okay, so it means the kth sample. So to formalize the Bayesian problem, the Bayesian filtering problem, we at every time instant k, you can define the following: the state vector xk, the control vector applied at time k minus 1 to derive u from xk minus 1 to xk. This is what we're going to be calling it uk. And the zk would be an observation taken from the state xk at time k. Okay. A lot of stuff, but actually it's very simple than just how it looks like. So whenever we start, so going back to this picture, when we start, we're going to be telling the robot we think you are in this location. So this is where the P, so this is X at time 0. So this is before we start. So this is just K equal to 0. This is time equal to 0. And we tell the robot where it is, not by telling it exactly where it is, not by just a state, x0, but we give it a probability function. And it looks like this. And then afterwards, we start to derive the robot. Let's say this is a robot that has wheels on it. How do we make it move? How do we make it locomote in the environment? By doing what to the wheels? Rotating the wheels, exactly. So each wheel will have maybe, for example, here this is just one wheel, assume just in 1D. So we give one wheel the value, okay, U1. We just give it, this is the signal to the wheel. So U1 here is the input that you give to the robot. So the velocity that you told the robot to move with, the wheel. And you give it at time step equal to 0, and you move to time step equal to 1. So here we're now in time step 1. So this is what this means. P of x1 given U1 happened. And then afterwards, in time step 1, you get a reading from the sensor. Let's assume that on the sensor, there was a reading, for example, there was a sensor, so on the robot, sorry, there was a sensor that measures the position. Maybe like a LiDAR or radar or something. Or maybe a very fancy GPS that tells the robot where it is in 1D. So this is just a special GPS. And it will tell the robot, it will give you a value. It will tell you the robot, so here for example, this PDF has a mean maybe at, it's telling you that the robot, I think it's at position 0.5 with some variance. But here the sensor is telling you the robot is at position 0.7 with another variance. So 0.7 plus or minus something, and here is 0.5 plus or minus something. If you combine both of these together by Bayes' rule as we just saw, you get that the robot will be maybe in between. Maybe it's not at 0.5 as what we predicted earlier. Maybe it's not at 0.7 as what the sensor told us. Maybe it's in between, 0.6. And you're more confident now because of this Bayes' rule. So this is exactly what you see here. Applied, what we discussed applied to this 1D robot problem. This is what we call the robot belief at k equal to 0. And this is what we call the robot belief at k equal to 1. Is this clear? So robot belief at k equals 0, robot belief at k equal 1. This is the step that we included with the U, and this is the step that made us include the Z. Okay. Now this is a little bit of a look ahead, so this box here, but I'll just mention it now, and we're going to come back to that later. Usually what we use in this step are the sensors that are inside of the robot, okay? That measure stuff that's inside of the robot. What are these sensors called?
Passive, not passive.
No, not passive and active. Another differentiation, another classification. What was it?
Receptive.
Proprioceptive, exactly. We call sensors that are used that measure stuff internal to the robot are called proprioceptive. Usually this is what we mean here by the U. Usually it's a proprioceptive sensor. I'm saying usually, okay? Because you can always play around with this, but usually this is the case. And the Z here, what do you think will be? No, the Z itself. What kind of sensor? Exteroceptive sensors, okay? So you see here, this framework will allow us actually to take the proprioceptive sensors and the exteroceptive sensor that you have on the robot, and you can combine them together to know where the robot is, okay? So now this is what we just discussed right now is only at time step 0 and time step 1. And the robot will start moving in the environment, right? Till infinity, technically, until it finishes its mission. So the robot just keeps on moving again and back and forth, back and forth. So the robot itself is running, the computer on it is running at time is equal time step 0 and time step 1, time step 2, and so on and so forth. So the algorithm that we want to build, we just wanted to advance from 0 to 1, from k minus 1 to k in general, right? We just wanted to advance like this. So as we move on, all of the positions, all of the states of the robot, we can just put them into a big capital X. We're going to be calling this the history of the robot state. And the history of the control inputs will be this capital U. All of the U's that happened up until now. And the history of all of the observations will be the capital Z. All of the small Z's that happened so far. Make sense? This is just some notation, but we're going to be relying on them heavily later on. And now to the important part, okay? So in general, this is the recursive Bayesian filtering algorithm. Okay? Recursively, you always start from somewhere like this, and what you want to end up is somewhere like this. So at this stage, how can you read this? You read this as the following. This is the posterior function. So this is the probability about the robot's position at time step k minus 1, given all of the previous observations up until now, and all of the previous inputs, all of the control inputs I give to the system up until now. So you see here, k minus 1, k minus 1, k minus 1. Clear? And here, from uk minus 1 to uk, there is something that was added. And it's only uk. It's the latest input I give to the system. Okay? So I give it the latest input, what I know, the uk. And this becomes now a probability function over xk, given all of the previous observations. I did not add any new observations. I just added here one small u to the big U that we had. And just to remind you, when we say big U here, we mean U1 up to UK. So big U at time step k is simply all of the inputs from 1 till k. Okay? So it's a set here of all of the previous ones just in addition to the latest one. The same also here. So xk is all of the previous states in addition to a new one. And here, all of the observations capital Zk are all of the old observations in addition to the latest one. Okay? So it's always this pattern. So here, I have a new input, the UK. I just updated, I added to this value, and I get this updated probability distribution function. And this is something that we know of the robot. Okay? We actually need this piece of information. This is not something that you can add to it. I'll come 1 second now. 1 second. Okay? So this is something that we always need. This is usually what describes the sensor itself. So when I buy a sensor, I always know that it will give me the reading plus or minus some value. Okay? The standard deviation, or in general the covariance of the sensor, always comes as a data sheet. You need to, when you buy a sensor, you always need to know how much can you trust this sensor. So this is usually given by this likelihood, and we can always add this likelihood to this function, and we can get a better update by adding the zk. Yes, ma'am.
So slide اللي بعده. أول معادلة فوق الدكتور.
Yes, this one.
في الطرف اليمين.
This one.
هنا لو افترضنا مثلا k equal to
10. Exactly.
فبيكون الهدف في القوسين اللي في اليمين أو المعادلة كلها بتساوي آخر حدين.
This will be x10, and this will be x from 1 to 9. It's a capital X.
Okay.
The capital X includes all of the from 9 to 1.
From 0 or from 1?
From 1. We'll just assume it's just from 1.
From 1 to 9.
From 1 to 9. So this capital X with a 9 down, capital X with 9 down, it means small x0. Sorry, this is from x0 here. So, yeah, so the U and the Z, they start from 1, but the X starts from 0. Okay, because usually this is like the initial condition. X0 is usually the initial condition. From x0 up to x9, this is what you'd see in here. And this is here x10. Clear? It's a little bit of, so this is just notation in terms of sets. What it means that is it's much easier than this. Look at it like here. X10, so let's see that you want to put X10.
Yes.
So X10, capital X10, is simply from 0, all of the small states, all of the states of the robot. So when the robot was here, when the robot was here, when the robot was here, and so on. So it's time step 0, time step 1, up until time step 10. If I take these alone and combine them into one bag, one set, what do we call them?
X from 1 to 9.
That's it. That's what this notation is. That's an excellent question. Because what we want to do here, usually this is what we do to actually write it in a recursive way. You see, the capital XK is the last value of the capital X itself, in addition to something, only one thing that's new. This is the same, with only one addition new. This is the same as what was before, and then you have something new. This is just the recursive way of writing it. Okay. You see? It's only just to put it into a recursive fashion. And that's exactly what you see here. So this is the prior belief, this is the posterior belief, but at every time step, and they are written as a recursive in itself. Okay? And in this step, it's called the prediction update. We add the UK, and in this step, we add the ZK. I'm going to repeat again what I mentioned earlier, that if this is the general way of doing the filtering. That's why this lecture is very hard, I know, because it's very abstract. I'm not giving you any algorithms. I'm not giving you any real problems where you see this, but this is foundation, what we're going to be building on 3 or 4 lectures. So this is very important. And that's why the video for those who came late. And thus, this step, we usually add into it, and this is what we're going to be doing later, we add proprioceptive sensors. And in this step, we add exteroceptive sensors. So at every time step to move from here to here, I already combined the proprioceptive sensors and the exteroceptive sensors, and I have a better estimate about where the robot is. And I keep just running in a loop and a loop again and again and again and again. So as the robot is moving on, again, let me give you an example. As you're driving with your car, the certainty of of where you are with the GPS keeps on changing back and forth, keeps on going. If you go, for example, near a building, it goes big. After you pass by the building, it becomes small again. So there's an always calculation of where you are. This is the recursion part. Okay? So going from every one step, from time step to the other, okay, you have this way of recalculating stuff. Okay. So now let's look at the two. What do we need actually to implement this? Okay. This is still, again, very abstract, but starting next time, inshallah, it will be more clear. So during the prediction update, which is going from step number 1, we start about a prior where the robot is, and we add to it the UK. What do we use to do that? You need to have something called a state transition model. Have you heard this before?
Yes.
Where?
AI.
Last semester, right, in the AI course. The state transition. Does anyone remember what the state transition model is? From last semester, not from in this context. What was the state transition model? Someone except now. Someone else. State transition model. Yes, man.
Probability of being at state or something like this. Being at state, another state.
Okay. Given what?
Given where you are, I think.
Given where you are right now. That's right. But what else? Yes. Exactly. We look at it in a tabular fashion. Remember that what we discussed in last semester in the reinforcement learning part, we had the probability table, the state transition probability. When you were in state S0, SK for example, and you want to go to SK another one, given what? There was always something given in the table.
Action.
Given an action, right? Does this ring a bell? I'm in this state. I want to go to that state given this action. Make sense? That's exactly the same thing. What's the only difference here? There's just one small difference between what we discussed here, what we're discussing here, and what we discussed last semester. Yes, ma'am. The U is the A. The U is the action. It's exactly the same. But there is something different. It's related to what you said, Omar. No, that's the same. Yes, sir.
We are noting the steps that we are considering.
We are?
Noting the steps of the situations that we take.
The recursive way. That was also, actually we had it there. Remember when we were looking at the reinforcement learning, we were always going from step k minus 1 to time step k. We always had the recursion, even then. Yes, Abdurrahman. We don't have any previous state. That's a good catch. We don't have, so going from xk minus 1 to xk, I'm not depending on xk minus 2 and xk minus 3 and so on and so forth. What do we call this property? It had a name. Markov property. So actually we're still applying the Markov property. That's also the same. So far it's exactly the same.
I think in that example in the AI was abstract more. It is only you either take this action or that. It's like policy.
I think you know what you just used the wrong word. I think you're correct. You're saying it's abstract. I don't think you mean abstract. I think what you mean is discrete.
Yeah, yes.
Discrete.
Yes.
So there, I had discrete actions. I was in a state. I had discrete finite number of states, finite number of actions, and that's why you had a table. But here is this finite states and finite actions.
You give control input, it could be.
So it's continuous, exactly. So that's the only difference. What we discussed before as the tabular way of looking at the state transition model was just if you have discrete probabilities, this is simply the continuous version of it. That's why we have functions. I have a function here that works for all x. X here is from minus infinity to infinity. Okay? So it's just the whole real number. Is that clear? So that's exactly the same as what we had before. So the key idea of the state transition model is that if I'm at xk minus 1 and I apply the action uk or the input uk, how can I predict where I am next? So xk. This piece of information, I can use it to update my prior belief into something new. So this is what we call here the prediction step. How do we do this mathematically is beyond the scope of this course. Actually, last time I gave the course, actually we included this into the slides. It was, I think, about 3 or 4 more of heavy mathematics. Actually, it's just using the stuff that we discussed, but for your sake, I removed it for you, okay? Just to make it easy. But this is the intuition. I just want you to get the intuition about it, okay? So, simply, this is an example. So, if the robot is at one location and moves forward for 1 second, then the state transition model will predict where it should be next. Okay? But not exactly, because the real systems are not perfectly, okay? They're not perfectly predictable. We have noise. Then simply, we have inside of this model uncertainty. So it's not that that the robot will tell you, I'm exactly in this location. It will also describe how the PDF itself changes. Okay? This is something we're going to be looking at it next time in details, inshallah, with an animation. But for now, you can already see it. If I move from one step, if I only move one step with the robot, it moves from here to here. The robot had a prior belief that it was here, and then afterwards, this is the belief above the robot, after it applied the action. Now, a question to you is the robot now, after this step, is it more certain or less certain about where it is?
Less certain. Less certain.
Less certain. How do you find that?
Because of the
The Gaussian is wider here. So before it was more confident. Okay? The GPS signal, inside of Google Maps was smaller. The circle was smaller. But after it moved one step, the circle got bigger. And that makes sense, right? If it's only relying on the wheels, and inside of the wheels you're telling it actually the wheels you cannot trust it, then it makes sense actually that you get, you accumulate errors as you move. How to fix that? What should we add now? We should use another sensor. And that's exactly the correction update step. So the correction update step is that now this is my prior. This is my prior about what I think I am right now. And this is where I think, so this is the likelihood of the sensor that I'm having. And I'm adding here now some sensor input, some observation. And then afterwards, I should get, from Bayes' rule as we saw earlier, I should get a better belief about where the robot is. Okay? So this is usually done by Bayes' rule in exactly the same way I showed you earlier. And of course, if everything is Gaussian, then things become easy. We can do calculations. And that's exactly what we're going to be doing next time. And that's it. So the correction update, prior belief is given by this purple PDF, the likelihood is given by the green PDF, and the posterior belief is given by this blue one, and it's a combination of both using Bayes' rule. Okay. And that's it. So that's it for the lecture, and that's the summary of what we're doing. You see what we did now, so what we have right now, so we went from this basics of probability, just about, talking about conditional probability, joint probability, and all of that stuff, and talking about just Gaussians, and we have now a framework. We have a way, actually, of, if I implement this on a robot, it's not clear how, but if there's a way, actually, I can convert this into an algorithm, a computer algorithm. When I implement this on the robot, I can always start from some sort of belief about where the robot is and do one update, one prediction using the proprioceptive sensors, using some input, and using also a state transition model, and I can get like a, it's not going to always be good. Actually, it's going to be just some extra, something better. It's actually better from starting from this. So you see, I use some input. There's some more information, even though I'm less certain about where I am. But after that, I correct this step. I correct it with another sensor. So U can be one type of sensor, Z can be another sensor. So actually, in this way, I fuse the reading from U and Z. I fuse the reading from U, from the sensor U, and from the sensor Z. And I have a better belief at time step K. So this is where I started with at time step K minus 1, and this is where I end up with at time step K. And then you move on. What happens? No? No. You move from time step K to K plus 1. So if at time step K, so let's say for example, from 0 to 1, this was 0 and this is 1. Now if I want to go from 1 to 2, what happens? I just do it again. What I just calculated as being the 1 becomes now the prior, and I apply again another signal. Okay, I go through the same loop, and I go to time step 2. And now you're done calculating 2. Whatever you had in step 2 becomes the prior of the next time step, and so on and so forth. So this is a recursive algorithm. You just keep on running again. Does it stop? This only stops when you turn off the robot. Okay? It's only when you turn off the robot that this stops. So it's always running inside of the robot. Okay? And this is the foundation of what we're going to be doing later for the localization. So this is how the robot will know where it is. It's not clear yet because we don't have an algorithm. Yes, Amr. Sorry? That's an excellent question. That's a really nice question. So I'll rephrase what Omar is saying. In order to go from time step K minus 1 to time step K, do I need to store everything else that happened so far? Do I need to have a huge so in other words, if you're storing inside of the robot, is the memory of the robot just keep on adding more sensor and so on and so forth? Do you need this to solve this problem? Do you need to store all of the previous history? Yes or no? You only need to have the prior, the latest information that you have about the robot. And you see here, I used here UK in this step, and I used ZK. And then that's it. When for example, did I use here UK minus 1 or UK minus 2? Did I depend on XK minus 1? Did I need to know where the robot was 3 or more time steps ago? What is this? This is actually based on an assumption. What's it called? What's the assumption that we made here? For this, what are we assuming here? We're assuming the Markov property. That the state of the robot in the next time step depends only on the current one. Not on what happened before. For example, what you're going to be doing in the final exam, how good you're going to be doing in the final exam, does not depend on what you did in the midterm exam. Right? So this is true, right? It's not an assumption. This is really true. This is what it is. Right? But for example, how much money you're going to be winning tomorrow, okay, depends on how much you invested yesterday and the day before and the day before and the day before. Never stops, right? Just if you invested 10 years ago, it can still affect how much you win tomorrow, right? So in this case, you cannot make this assumption. But in case of robotics, we always do this assumption. Moving from time step from one to the other only depends on the last time step. And thus, we wrote it in this recursive way. And the only thing you need to store inside of the robot is actually the state transition model and the sensor model and everything, and all, of course, all of these PDFs. Now, a very important question that follows from that, Omar, is that how do we represent this Gaussian inside of the computer? Sorry, actually, I answered the question. How do we represent this PDF? How? The PDF is a function, right? How do you save this function? That's for the next lecture. So that's the starting point of the next lecture, inshallah. Okay? Any more questions? Okay, I think that's it.